It seems that it's 2 p.m. here, so it's time to start. So hello and welcome to the Future Challenges in the EAF Steelmaking webinar. My name is Antti Lassila and I am the host of this webinar. First, some practical matters. You can ask questions during the webinar. This can be done by using the Questions tab in the webinar software. The window should be on the right side of your screen and it looks something like this. The questions will be discussed in the last part of the webinar. Link to the recording will be sent to you after the event. About the speakers. We have two speakers today, Professor Timo Fabritius and Dr. Matti Aula. Professor Fabritius is the head of process metallurgy research unit at University of Oulu. He has published around 130 journal publications and over 100 conference papers. He has also led several large programs and projects in Finland and internationally in the field of steelmaking. Dr. Aula is the head of research at LuxMet. He has around 10 years of experience in measurement technologies in steelmaking, especially in electric arc furnaces. Dr. Aula has a doctoral degree in process engineering. The time schedule. In the first part of the presentations, Professor Fabritius will discuss the rising trends of EAF steelmaking. In the second part, Dr. Aula tells us about real-time dynamic EAF control. In the last part, they will answer your questions. Okay, Timo, go ahead.
Thank you, Mr. Chairman. I will now share my screen. And I hope it's working now. Yes, my name is, okay, thank you. As Chairman introduced, my name is Timo Fabritius and I work as a professor of process metallurgy since 2010, and now I will have a short 20-minute presentation concerning the rising trend. My presentation will start by the short introduction of European low carbon roadmap in steelmaking, and then I will continue the role of electric arc furnace in the future and what kind of pressure there will be in concerning on the increased production costs because of the transition to low carbon metal production. And then some slides concerning on the energy sources and energy balances. And finally, I will shortly introduce the development what is the situation of the electric arc furnace technologies development, and then finally summary. If you look at the overview of steelmaking roads, here in the left side, you can see the traditional integrated road starting from the ore, which is used as a raw material in blast furnace and then converted as a steel in BF-BOF converter. And in the center of this figure, here's a smelting reduction processes, again using lumpy ore or ores as a raw material and then converted in the metallic form by fluidized bed or melter gasifier units, and then continued by hot crude steel production by BOF converter. But today we are more interested in the production by electric arc furnaces, and here we have two different kind of raw materials which are possible to utilize. The electric arc furnaces are using scrap as a raw material, but in the future we can see that the proportion of the oil-based raw material, for example, hot briquetted iron or direct reduced iron will have a stronger.
Timo, sorry to interrupt you. Can you check your mic? It's cutting your microphone.
It's cutting.
No, it's okay. Yeah, please continue.
Okay. Sorry. If we then go to the low carbon roadmap in Europe, European steel industry has an ambition to cut CO2 emissions 8 to 95% by 2050. And here in the picture, we can see situation 1990. We had in Europe approximately 200 million tons crude steel production, producing approximately 300 million tons of CO. And the estimates for the forecast until 2050, we have estimated that there will be an increase of production of steel, or it will be quite same as 1990, but there is a huge need to decrease CO2 emissions only so that there will be only some tens of millions tons of CO2. And based on these forecasts, we can see that there is no one solution to decrease remarkable CO2 emissions. So it means that both blast furnace converter-based and electric arc furnace-based process chains are both used, but the proportion of electric arc furnace is increased in coming years, and the role of the electricity, natural gas, and hydrogen will be also remarkable in the future. And it is also important to notice that there is a need of additional energy, about 300 terawatt hours per year, that has to be produced without CO2 emission. Only by this way, this kind of ambition to decrease CO2 emissions is possible to achieve. And then we continue the estimation of the production structure in Europe, achieving these very challenging CO2 emission reduction targets. It requires transition to new breakthrough technologies, which can be, for example, hydrogen-based DRI used in electric arc furnace. There could be top gas recycling in the blast furnace, and then also carbon capture and storage and carbon capture and utilization. But we can see that the role of the electric arc furnace will be bigger than today, so that these estimations based on the scenario that approximately 60% of steel production based on the electric arc furnace process. And if you look at the scrap availability in Europe, we can see that the scrap plays very important role in European Commission strategy and the European companies' strategy to decrease CO2 emissions. We can divide the scrap in 3 parts, so that there is a home scrap, which is generated in iron and steel production, and this amount of this and the volume and the quality depends on the production processes. And then we have a prompt scrap, which is generated in production of steel-based products, and again it depends on the production processes. And then finally, for the third part, we have a absolute scrap, which is available from the end-of-life products and applications. And this depends on how much we have this kind of scrap. It depends on the recycling rate of the scrap. And we can see that these scenarios based on the estimations that the volume of the home scrap, here figure, and volume of the prompt scrap will be the same in the future, but this absolute scrap will be increased. And due to aimed CO2 emissions, cutting competition of scrap is intensified globally as well. So that it is not, there will be a stronger competition concerning the scrap, not only in Europe, but it will be a global trend. And there will be also increased challenges of quality of scrap, so that I mean the chemical quality, how much there is impurities, for example, and also concerning on the physical quality. So what is the size of the scrap, so that it is suitable for the electric arc furnace process. If we look at the estimations of production costs in Europe, we see that there is a very high pressure of production costs increase due to the development and implementation of low carbon steel making processes. And replacement of blast furnace BOF converter rod by electrical furnace based one will increase operating expenses approximately 10 to 35%, depending on the raw material which is used in electric arc furnace. And for example, in case of SSAB, who has launched this hybrid project together with the joint companies, they have indicated approximately 25% higher production cost compared to current process chain. And development of new processes, including the carbon capture and utilization, must be started soon, because the investment cycle is so long in steel industry. So we have to start to develop and implement these new processes to achieve this target to decrease remarkable CO2 emissions in Europe, also in the world. If you look at the portfolio of processes and energy carriers in steel making in global scale, here on the left side, we can see that 2019, approximately 70% of steel is produced based on the commercial blast furnace BOF road, and approximately 20% by scrap-based electric arc furnace, and less than 10% by commercial DRI. If you look at the estimations concerning 2050, we see that there will be approximately 60% of production will be based on the electric arc furnace road.
Timo, sorry to interrupt you.
Or the scrap as raw material is very. Excuse
me.
Check the
mic? Can you check the mic again? Microphone.
Okay.
Yeah, it's better now.
Is it better now?
Yeah.
Okay, sorry, I will. Okay, good. So in the future, a scrap-based electric arc or scrap as a raw material will be the very important, of course, but there will be also increased amount of 100% hydrogen reduced, direct reduced iron used as raw material as well, and then these commercial DRIs using natural gases with and without carbon capture utilization together, so they form approximately 60% of the production in this scenario. And we can see that the low CO2 low or CO2-free energy will be very important to achieve these low carbon targets. But it's not only the reduction process which will be changed, but also the slack and sidestreams will be changed composition of because of the transition from blast furnace BF road to electric arc furnace. If the hydrogen reduced iron is used as raw material, it will dramatically affect on the slags and dusts and sludges which are generated in a steel plant. And in the future, if electric arc furnace will be the main unit to be used internal circulation of slags and dusts and slags, recycled refractories, this will affect also very much on the control of side streams. If you look at the energy balance of electric arc furnace, we see that approximately 50% of energy is utilized steel melting, and the off gases and cooling of the furnace are the largest losses, having together nearly half of the energy used by these two ways. And if we look at the input, we see that the half of the energy could be based on the exothermic chemical reactions with oxygen, and then if we are using DRI as a raw material, it means that that we will need some more carbon or reductant, more to reduce FeO, which are partly in DRI. And if a secondary raw material briquettes are used in electric arc furnace, then as a way of internal recirculation, then energy consumption will increase as well. Here we see the energy sources which can be used in electric arc furnace today. Carbon is the most important energy source, and of course the easily oxidated elements like silicon, aluminium, titanium in scrap, they could be utilized as an energy input to the electric arc furnace charge. But natural gas may replace energy, electrical energy, and it also lowers CO2 emissions compared to use of carbon or coal or coals. But it is important to remember that energy efficiency is dependent on the status of the scrap melting. So that with high scrap height, the utilization rate is higher and better. But today there is also a started discussion concerning on the use of hydrogen also as an energy source or the reductant as well. If we continue with the DRI, we see that the use of DRI will increase the demand of energy, and it depends on the metallization degree and carbon content of DRI, and there will be also higher slag amount because of the metallization is not the 100% in DRI. And we have to use more slag formers to balance silicon load in electric arc furnace. If you look at the material balance, we see that if we are producing 100 kilogram or one ton of steel, we have to approximately 1100 kilograms of scrap or alloys. But if we replace scrap by DRI, it means that also more slag is generated, and also specific energy consumption is higher. And this increase, it depends on how much DRI is used, or if the ratio of low quality scrap is increased, or if the electric arc furnace is used as an internal recycling unit. It's all of these, they increase the amount of slag produced during the melting. But it also means that there is we have to develop the process and monitoring methods so that they will be more flexible with the different raw materials and the different energies sources in the future. If you look at the evaluation of electric arc furnace technologies, we see that there is a remarkable decrease of energy consumption, electric energy consumption during the years, and also that the time has decreased dramatically, and the electrode consumption is also decreased, so that we are now working with quite low values. So the evaluation has been very strong and comprehensive, but due to total requirements concerning on the specific energy consumption and then higher production rate, we can see that the online monitoring methods are required. And since 2010, optical measuring methods have been developed also for electric arc furnace purposes, and it's also very good notice that artificial intelligence as tool in electric arc furnace process intensification is coming more and more important. And finally, I will summarize by this slide, so that transition from blast furnace BOF road to electric arc furnace based steelmaking is happening due to decreasing CO2 emissions, or the targets to decrease CO2 emissions. And if you look at the reduction of energy demand in electric arc furnace, it is possible to make by having more flexibility for the energy sources, to use hot charging, to preheat of scrap, to have a continuous charging of the scrap for raw materials, with the operating practice optimization, or by the optimal arc length, so that we can reduce the heat radiation from the arc to the walls in the room. Of course, increased.
So, Timo, sorry to interrupt you again. Can you go back a couple of points and no, the summary slide, like 10 seconds back in the last slide. Yeah.
Yes.
Yeah.
Sorry, so I start again. Reduction.
From the reduction of energy demand.
Okay, sorry. I'm very sorry of these difficulties with the noise or the voice. There is a need to reduce energy demand in electric arc furnace, and there's many different kind of possibilities to tackle this challenge, by more flexible use of energy sources, by hot charging, by preheating of scrap, by continuous charging, or by
Timo, it seems that there's some technical challenges again, so.
Okay, so maybe I can say thank you very much, and give a floor for the next speaker. Thank you very much.
Thank you, Timo. So it's time for Matti. Yeah.
So thank you, Mr. Chairman. I hope you can all see my screen.
Yes, we can see it.
Oh, good. Okay, so good afternoon. My name is Matti Aula, and I'm today talking here about the real-time dynamic control of EAF. And so thank you, Timo, for interesting remarks about the trends of the EAF. And here I'm trying to answer the questions that how has these trends been addressed in the past, and how they will be addressed in the future. So let's start from the electric arc furnace process. So as we all know, it's a process to melt the scrap, basically. So what we want to melt the scrap and generate a melt which has the optimum temperature and composition. So if you think about what can we control in electric furnace, many of the parameters are related to the scrap and its melting. So in the early parts of EAF process, the electrodes bore into the scrap, and then when the electrodes are inside the scrap pile, we can input the maximum amount of power because all the scrap is shrouded in the arc and all the sides are clear. I mean, sides are covered by the scrap. So most of the energy inserted in the furnace will stay with the steel. And then at some point, the scrap on the sides will melt down, and the sides and the roof parts will start to be uncovered. And this has serious consequences for many different electric arc furnace equipment. So for example, one thing is the electric arc furnace arc power. So when the sides are getting uncovered, we need to either lower the arc length and power or start the slag foaming to shroud the arc in the foaming slag to prevent the refractory wear and loss of energy. And on the other hand, if you use a multiple basket charge in practice, when the scrap's melting down, you would like to insert the second basket or third one. And you want to do this as soon as possible, as it fits safely, because then you can make sure that there's electricity efficiency is maximal. And then when the scrap has molten, there are some flat bath conditions. And in these conditions, usually many factories utilizing or making carbon steels utilize oxygen injections to foam the slag. And in this phase, it's important to control the amount of oxygen to carbon, so that we get as much as possible energy out of the carbon, but still we don't over-oxidize the slag. And in the end of the process, there is going to be steel and slag formed. And in the end of the process, we want to know that when is the optimum time to stop the process. So first of all, we need the steel to be of right composition, but it also needs to be of right temperature. So we don't want to overheat the melt or underheat it. These both will lead to serious consequences. As we see from this picture, a lot of these different control variables are related to the scrap melting. So I will be talking a bit more of that. So when you measure the scrap melting, the most conventional method to do that is just to observe the kilowatt hours that you have put to the furnace compared to the charge amount in tons, for example. Another very traditional method is just to hear the furnace. When the arcs get uncovered, the voice of the furnace starts to increase. And subsequently, if you start the arc foaming, the noise of the furnace will start to go down when the arcs are covered with the foaming slag. And also, one method which practically every furnace uses is this cooling water energy flow. So basically, we never want our side panels to overheat because this causes a serious risk of water leaks, which can be critical and even catastrophic in some cases. Yeah. And also, the state-of-the-art methods, or the coming things, or the best available systems, let's say, many people use these arc stability parameters to assess the scrap melting in furnace. So because in flat bath phase, the surface will start to, the slag surface and steel surface will start to calm down. There is not so much movement there. There is also not so much scrap falling into the arc. So because of this, the arc gets more stable during the end of the scrap melting. And this is often used to define the end point of the scrap melting, on average, on a furnace. And a solution that we are here presenting Our solution is to use the light emitted from the furnace to measure the scrap melting. And I will now tell a little bit more about this method of analyzing the light from the furnace. So when we talk about analysis of light and optical emissions, we are talking about the radiation that our eyes can see. And there is a lot of information in this spectrum. So basically what we do is that we measure the light from the furnace emitted from certain areas. We transport it to the spectrometer. We break it down to the different wavelengths. And by analyzing these different wavelengths, we can tell a lot about the process which sent this light to us. For example, if we are seeing just the cold scrap, we only see dark current, no light, because the scrap is shrouding the sides. And when the scrap starts to melt, we will start to see increased amount of thermal radiation, because the arc radiation will start to heat the surfaces. And also, sometimes we see alkali peaks, which are related to the burning material in the furnace. We will go back to this a bit later. And also, if we see the arc itself, the arc light itself, we also see a lot of atomic emissions coming from the hot plasma. So what we do is that we place some measurement heads on the furnace roof. Usually we use three measurement heads, depending on what we want to see in the furnace. We gather the light which is emitted from the furnace. We transmit this light to the remotely placed spectrometers. So we have no active equipment on the furnace roof. We can be sure there's nothing in these hazardous conditions. And when we have obtained this spectrum, we analyze the spectrum with our software, our homebrew software, and then we present this information either to the operators themselves, to the user interface, or we can also use this information directly to control the EAF process dynamically, straight away through the field bus, for example. So I was discussing earlier about these different types of spectrum. So many people ask that what is the relevance to the process actually? And when we talk about the light coming from the furnace, it's actually quite important to know that what we are actually seeing. Because oftentimes, for example, if your off-gas temperature rises, it can be of many reasons. But the biggest thing to separate in the data is to know that is it coming from the flames or from the slag surface? Because we never want to mix up flame temperature to the actual melting of the slag. So in this way, with the spectrum analysis, we can filter the data to contain only the information we need in a process control, and we don't make false assumptions of the melting or some kind of combustion reaction occurring in the pre-board furnace. Yeah, this information about the scrap melting can be used in many ways, just like we were discussing in the beginning about the furnace. So, for example, when the scrap melts, we can optimize the timing of the voltage taps. So when the scrap melts, we can reduce the taps. On the other hand, we can also time the burners and also injectors based on the scrap melting. Like Professor Fabritius mentioned, these burners should be operated only when there's solid scrap there. So if the scrap starts to melt and the burners are not burning to the inside the scrap, the efficiency of the burners will degrade highly. So you want to be shutting down the burners when the scraps start to melt, or it's near the end. Yeah, and also this information can be used in timing of the second basket charging. So you can put the basket into the furnace as soon as safely possible. Yeah. So when you talk about the online OES and also other methods, they of course they complement each other. We cannot say that this is method for everything. So what our system is good and especially good for is measuring the local scrap melting and also early scrap melting. So we know all these different phenomena related. Okay, has the hotspot of the electrode arm or the hotspot of the electrode been exposed? Is there arc radius from the hotspot? So we can directly control the process when the light or the scrap melting has reached certain early level. Okay, so I have been talking about our technology and the scrap melting in general. There are also a lot of other things that we can control with the process. And one control system which practically every furnace has is the electrode regulation system. And in this electrode regulation system, there are two different levels. One is this, let's say, dynamic fast control level. So this electrode arm position is controlled according to the current and voltage fluctuations. So for example, if the scrap falls to the plasma, we want to change the position of the electrode arm so that the arc length stays the same approximately. So this kind of control is fast, it's ongoing, it's usually done with PD control, with the hydraulic actuators. And then furnace also utilizes this like long-term or mid-term control, which is this transformer tap control. So what is the correct transformer tap to use in this phase of the process? So normally furnaces have this tap profile which they use. Usually there is some like set profile with kilowatt hours per ton, but usually these kilowatt hours per ton should be also modified according to scrap melting. So you have a certain kind of like assumption of the scrap melting which you modify the dynamic information about the scrap. And in this scrap melting, you can use our systems to time the voltage ramp, so that when you know that these electrode hotspots are exposed, you know things to do. And the other major source of automation in a furnace is this injection and burner control. And usually what can be done in the EAF is that when does this end and start? And for example, start of the foaming period is usually it's done by operator, because oftentimes it's done from the slack door. And this is the conventional way. So the operator looks in the slack door, okay, starts to burn the scrap out of there and says, okay, there's a pool. Let's start foaming. But also there are other methods to do this. And for example, we can use electrical parameters, for example, THD, meaning the arc stability, to estimate, for example, that if our arc stability is already high, we know that we are close to flat path, then of course we should not use the burners again. And also a very important method in nowadays to use in EAF control is this off-gas analysis, because this ratio of carbon injection to oxygen injection needs to be in certain range, and it's extremely difficult to define this range without knowledge of off-gas. So with this off-gas analysis feedback loop, we can directly control the injection amounts and the rates to get the maximum of energy out of the injected oxygen and carbon. And also this light analysis can be used in this timing of the, for example, the burners. So if you for example see that the burner flames are already in the air for the freeboard, of course you should not use the burners anymore. It's too late for those. And when the process starts near its end, there is going to be a question of, is the melt already ready for tapping. And now we are talking about what is the melt temperature and what is the melt composition. I think the most conventional method to do this is to get a sample probe and put it to the furnace and check temperature. This is the, let's say, the conventional method. And in the recent years, there has been a lot of interest in these robot probes. So instead of operators doing the probing, we can have robots to do this for the operators. This has two different advantages. For example, the position of the probe is more uniform with the robots, because it of course depends on the operator what is the height of the push. And the second thing is that of course nowadays we don't want the operator to be too close to the furnace. It can be sometimes cause some health hazard. And in the future, when we talk about how to tackle these different requirements of the EAF process, we need to also improve this endpoint control. And there has been quite a lot of development in this section. For example, there are coming things like online temperature control. There are certain fiber optic measurement system, for example, which can be used to feed fiber to the melt. And also there has been lots of research concerning online slag composition analysis. So we are also doing our analysis. We are doing this arc emission control, which we are developing. And also there are other methods to do this. For example, LABS, laser-induced reflectance spectroscopy, is another interesting avenue of research concerning this. And when we talk about these future challenges, and how could we make the furnace even more efficient and CO2 friendly? So big thing concerning this is the definition of the endpoint of EAF. There has been a lot of research and development concerning this topic. But the problem with many of these models and such is that they are only that good as the data they are trained with is. So we need these new methods to get more and better data for this automatic control. And we also understand that this integrating different sources of information is very important in furnace control. And we are also actively working in cooperation with University of Oulu, with Professor Fabritius, and also with RWTH Aachen in developing these kind of process models, control models. And just quickly about these control models, there are two main groups of control models. There are statistical models, which basically are trained. So we throw a large amount of data to a code, and the code tells us what is the result. And this method is very good in accuracy. We can say that it's the best it can be, because we can use in like 100 different parameters. But the trouble in this approach is that the teaching and the training can be very, very narrow. So even 1 week later, it can be that the model is not good anymore, because the teaching data is already obsolete. So these kind of models require constant tuning. They are quite heavy in the maintenance perspective. The other method to use in this kind of model approach is to use process models which try to replicate the physical and chemical processes occurring in the EAF. And this kind of approach it requires much more coding, of course, because you are trying to model the phenomena as they are. And also the second thing is that they are never just as accurate as the statistical models. But the good thing is that they are usually reasonably reliable, that they don't suddenly drift out of the information of the area. So they don't usually give like completely strange answers. So they are quite useful in like this kind of reliable control of the electric arc furnaces. And if you want to know more about these model developments, there are 2 different papers that you can read if you want. We have done one review article with the University of Oulu concerning these mathematical process models. And also Mr. Professor Odenthal made also a very good review article on this different type of model and simulation approaches on electric arc furnace. Yep, and in the end, many of you have heard for sure about these machine learning and AI applications. It has been a long talk and long road in electric arc furnace. One could say that this development of these methods in EAF has not always been very fruitful. But I think that nowadays we are reaching the state with the data we have that it's gonna be reasonable and it's gonna be relevant in the near future. And always with these machine learning systems, it's quite important to know your application. So one way to use these machine learning methods is to use them to tune the control function parameters of the electric arc furnace. For example, when I talked about these statistical models, they have the problem of drifting always out of the scope. But if you tune the control parameter of these models with let's say kinetic algorithms, you can continuously update your models. And if you are using such a model, this is a huge saving of time, because the engineers don't have to be checking the models all the time, or the control systems don't have to be adjusting a PID control, but you can do it automatically with a systematic way. And the second thing which will be important in the future, I think, is the endpoint estimation, and definitely steel temperature and also some point composition. But this is a in connection with the sensor development. So as the sensor development increases and advances, we can increase the accuracy of these endpoint models. We are not there yet, I would say, that we can completely estimate endpoint temperature, but this is the direction that we are going in the future. So in summary, a big shift in electric arc furnace steelmaking is that the conventional method of operator doing all the control functions, let's say timing of the carbon injections and such, you are switching from this operator controlled to computer assisted. And what I mean by that is that now the operator does all the actions, all the thinking, a lot of the thinking. Operator hears the noise of the furnace, okay, checks how it looks like, and makes a decision. But in the future, the code is going to be making the suggestions. So these models and control systems will tell the operator, okay, now would be a good time to start, let's say, second basket charge. And then it's up to operator if he wants to believe it or not. But the thing is that it's not anymore an active decision by the operator to decide this time. And also, I want to emphasize that this light analysis system that we utilize, it's a very good tool, especially for the measurement of scrap melting and control of the different parameters which are linked to that. And also, when you compare and combine the data from different sources, in future, I'm sure we can obtain even more accurate furnace control. And I sincerely hope that we can meet all those demands that Professor Fabritius was talking about for the requirements for the electric arc furnace control and efficiency. So thank you for this presentation. So, Mr. Chairman,
thank you. So now it's time for questions. We have a couple of good questions here already. So you can still send some questions if you have any, and I will be then forwarding them to the presenters, Matti and Timo. So the first one is for Timo. Can you read it aloud and answer it?
Yes. Sorry, I will open this. Yeah, I'm really sorry about the problems with the noise or my voice during the presentation. I hope it's now better. So the question is that how do you see the importance of hydrogen-reduced DRI as a raw material in electric arc furnace? Yeah, if you remember from my presentation, there was an estimation that approximately 5% of production, global production in 2050 will be based on the hydrogen-reduced iron. And okay, it's 5%, or the estimation is that 5%, but if you look at the volume, it's still some more than 100 million tons of steel. And I believe that it is it has there's a regions where this hydrogen reduced iron would be a big player, so that if you have electricity without CO2 emissions, or the electricity which is produced without CO2 emissions to produce hydrogen by nuclear power or by hydropower, so you can produce DRI with hydrogen, and then it can have a global, regionally it can have a very big role, but in a global scale it will be maybe some percents. And of course, at least in Europe, we are speaking very much about a hydrogen economy, and let's see how it will be realized. But I believe that we are all sure that it takes at least some 10 years or more, so that we really have a first industrial scale hydrogen-based reduced iron as a raw material in electric arc furnace. So regionally it could have a role, but globally maybe not so big one.
Thank you, Timo. This one is also for Timo.
Yes, could induction furnaces become a competitor of EAF or continuous reduced furnaces, SAF, or already induction furnaces are built with 40 megawatts? So yes, I believe that depending on the raw materials which are used and energy sources, that there could be possibilities that the electric arc furnaces maybe induction furnaces are not so big player, or will not have so big role. But maybe in some cases, if you have a raw material more suitable for induction furnaces. But still, I believe that electric arc furnaces or the shaft-based furnaces will be the key processes to produce steel and ferroalloys.
Thank you. Matti, can you take the next one?
Yeah, so we got a question here about the DRI. So the question is following. So have you considered testing LuxMet technology in continuously charged DC furnace with DRI? And could you give interesting results? So concerning this, with the DRI, we are currently looking for the furnaces to test this currently. So we have no concrete results on the DRI DC furnace yet, but that is definitely something which we find interesting because in the heating of the bath and the melting of the DRI, the temperature of the DRI is important. It always varies. So we assume that there is high variation of DRI melting, which we see that it could be an interesting control parameter for us in the future.
Yes, there's second question about arc spec too. Can you, Matti, see that?
Yeah, so the question is following. So how many arc spec sensors are required or recommended to install in the EAF hood with capacity of 150 tons? So the amount of measurement heads or sensors depends a bit on your furnace type. So if you're operating with an AC furnace, I would say that if you want to measure or control the basket charging, and you need to know the melting in the hotspot regions. So typically with the AC furnace, we use 3 heads. With DC furnace, you have a little bit of more room because the hotspots are not so less defined. So with DC furnace, the most important thing is to put your head in the hotspot of the furnace. So typically on the arm side of the furnace.
Thank you, Matti. Timo, the next one is for you.
Yes, I have a question concerning on the refractories. So, and the question is that what impact do you think these trends will have on refractories, maybe greater wear, and what should refractory producers consider going forward? Starting first on the effect of the trends on the refractories. Yeah, I believe that there is a increased demand concerning on the quality of the refractories, because if the furnaces has to be more flexible with the different raw materials and maybe with the low grade scraps, and if they are using more DRI, having higher silicon or silicon oxide load to the furnace, so there will be more chemical attacks to the refractories. So that is, I believe that there will be more demands concerning on the control of the refractories in the future. Maybe it's not only concerning on the slack height or the slack area, but maybe also for the lower part of the furnace. And what should refractory producers consider going forward? I believe that the control of the cooling of the refractories will be becoming more important, so that if there's a possibilities to generate autogenous refractory layer at the refractory surface, then it could help the refractories to have a longer campaign life for the refractories.
Thank you, Timo. The last question for Matti, and it seems that we have quite many questions here, so we are going to answer these after the seminar, and we are going to email this. But Matti, go ahead with the last question.
Yeah, so we have a good question here about the protection of arc spec sensors. So the question is following. So what is required to protect the arc spec sensor during the operation? And second question is, what is the lifetime of such sensor? So this is an important point to which we have given a lot of thought and a lot of development. So because every one of you know that the electric arc furnace is a very hazardous environment. So because we only use passive systems there, basically fibers or pneumatic systems if required. And we usually, of course, we cover the whole system with insulation, and usually also we cover the system with the steel to protect for the electrode parts or the scrap flying. And of course, there is a constant purging gas to keep the view cone open and also to cool down the head. So by combination of purging and insulation and protection, we can make sure it's actually it withstands well the conditions. And concerning the lifetime of such sensor, I would say that the lifetime of sensor on the roof, I would say it's 1 year typically. It is not in 1 year it's not destroyed, but in 1 year you have a degradation of the fiber coating a long time. So the light level can start to creep down in long time, let's say 1 year. So we recommend our customers that we change the furnace cables at least once a year. But the other cables, we have experience of using the other cables for multiple years. So.
Thanks, Matti. It seems that we have used our 60 minutes, so that's all for today. We will be answering the rest of the questions after the event. We'll be sending you an email. But thanks for you all for joining us, submitting the questions. If you want to discuss with us about EAF optimization or have any questions, feel free, send us email or contact us through the website. Thank you and bye.
Thank you.